Hello and welcome to the AI Research Roundup. I'm Alex and today is May 15th, 2025. Alright, today we are looking at a research paper from Hugging Face's trending list, published just 3 days ago, titled MiMo, Unlocking the Reasoning Potential of Language Model, from Pretraining to Posttraining. This paper introduces MiMo 7B, a language model with 7 billion internal settings, designed for strong reasoning. The authors optimized both its initial learning, or pre-training, and its later refinement, post-training. During pre-training, they used a special training goal called multi-token prediction. For post-training, they employed reinforcement learning, a method where the model learns via rewards to boost math and coding skills. So, to give us a visual, this first figure presents 2 line charts. The left chart tracks performance on Live Code Bench version 5, a coding benchmark, while the right one shows results for AAME 2024-2025, a math reasoning test. The orange line, MiMo 7B after reinforcement learning, consistently trends upwards, outperforming other models. The vertical axes, AVG at 8 and AVG at 3.2 respectively, measure the model's success rate given 8 attempts for code and 32 for math. These charts clearly illustrate MiMo 7B's strong reasoning capabilities improving with more training. Okay, so building on those performance improvements, this next figure, figure 2, shows us how the authors implemented a key technique called multi-token prediction, or MTP. Multi-token prediction is a method where the model tries to predict several upcoming pieces of text, or tokens, all at once, rather than just the very next one. The diagram details the main model architecture on the left, with these MTP blocks branching off. These blocks, shown in more detail on the right, help accelerate inference, that is, the speed at which the model generates responses, and improve overall performance. Alright, so after looking at how multi-token prediction works, this table, Table 1, really drives home the impact. It compares MiMo 7B base, the initial version of the model, against other similar-sized open-source models across various benchmarks. These benchmarks are standardized tests for AI, covering general knowledge, math, and coding. We see MiMo 7B base often leading, especially in math and code, like on AIME and Live Code Bench. The shots column shows how many examples the model gets, with 0 shot meaning none. And pass at 1, seen with some benchmarks, indicates the percentage of problems solved correctly on the very first try. Okay, so moving to figure 5, this visual really unpacks their experiments with what they call a test difficulty-driven reward. On the left, bar charts show how test cases are categorized by difficulty, easy, medium, or hard, for 3 model setups based on each model's test case pass rate on them. A test case pass rate is just the percentage of tests solved correctly. Then, the line chart on the right shows performance on Live Code Bench, comparing different reward schemes, essentially different ways of giving feedback during reinforcement learning across numerous training steps. This comparison highlights how reward strategies affect learning. Now, after seeing how reward strategies influence training, Table 4 gives us a broader picture. This table compares the final MiMo 7 BRL model, the one refined through reinforcement learning, against several other well-known models. It covers general knowledge, mathematics, and coding benchmarks, often using that pass at 1 metric, success on the first try. We can see MiMo 7 BRL holding its own and frequently outperforming others, especially in math with scores like 55.4 on AIME 2025 and in coding with 49.3 on Live Code Bench version 6. This really underscores the success of their holistic approach. Following that comprehensive comparison in Table 4, this next table, Table 5, zooms in on the MiMo series itself. It evaluates different versions of the MiMo 7B model, the base version, one with just reinforcement learning called RL0, another with supervised fine-tuning, or SFT, which is a process of further training the model on specific examples to improve its performance on particular tasks. And finally, the full MiMo 7 BRL. We see across math and code benchmarks, like Math 500 and Live Code Bench, that combining supervised fine-tuning with reinforcement learning consistently yields the best results, really underscoring the value of that supervised fine-tuning step. Building on that point about supervised fine-tuning, the overall conclusion with MiMo is that a holistic strategy is paramount. This means careful pre-training, using techniques like multi-token prediction combined with robust post-training. For instance, their reinforcement learning used a method called group relative policy optimization, which helps the model learn by evaluating sets of its responses. This comprehensive effort is what allows these smaller 7B parameter models to achieve such strong reasoning, rivaling larger ones. That's all for our look at MiMo today. I'm Alex, thanks for tuning in to the AI Research Roundup.